Hi, in this lecture we're going to be talking about the big boy of all the matrix decompositions, which is singular value decomposition, or SVD. It's arguably the most important matrix decomposition that we'll be talking about in this entire linear algebra review section of the course, and will be used quite a bit throughout the course. It's definitely good to know your review at this point. This goes to chapter 2.8 of the Deep Learning textbook, so make sure to read that after watching this lecture. SVD is a bit of a tough topic to cover since it's so nuanced and requires a lot of prerequisite understanding and kind of a deeper understanding that I provided in this review. So I won't be able to cover it as deep as perhaps you could cover SVD. A lot of times the first time you learn SVD, it can be like a multiple-hour endeavor of talking and exploring the different nuances of it. But I'll be trying to cover it kind of maybe in less than 20 minutes or so. I guess there's kind of two big ways to tackle learning about SVD, and I'll be doing it in a slightly more quicker way, but still trying to provide some geometric intuition and some algebraic intuition along the way. A lot of it that I've gotten from Gilbert Strang's several lectures on the topic of SVD, because I found a lot of his techniques in describing these things were really good at kind of simplifying the intuition, but still making it clear why the SVD algorithm looks like the way it does. So I credit him to a lot of these intuitions that I'll be describing throughout this video. Okay, so after all that's done, let's get started. The powerful thing about SVD is it basically extends what we could do with eigendecomposition for square matrices to any size matrix A. So now we can decompose some A into three-component matrices even if A is non-square. And this is helpful because often in data science and machine learning, our data is not compiled neatly into square matrices. It's often in rectangular matrices, which is why we often use SVD even more often than eigendecomposition. Okay, so I'm just going to throw up the formula for SVD, and then we'll slowly deconstruct what it means throughout this lecture. Okay, so basically, the formula itself is simple. So we can decompose the matrix A into three-component matrices, just like we did with eigendecomposition. This time those matrices are U, D, and V transpose. And we still don't know what's in those matrices or how we compute them, but we'll talk about that shortly. But first, let's just talk about what type of matrix each of these matrices are. So this U is going to be an orthogonal matrix, which means its columns are going to be orthonormal to one another. So that's going to be an orthogonal matrix. D, again, is going to be D is going to be a diagonal matrix. And V is going to be another orthogonal matrix. So orthogonal, diagonal, orthogonal. And now we can come up with some terminology of what the columns of each of these mean. Remember in eigendecomposition, we could decompose some A into some U, lambda, U transpose. Remember? And the columns of U were the eigenvectors of A. And the elements in the diagonal in the lambda were the eigenvalues of A. Similarly, in this, we have a similar way to kind of organize these things, but instead of eigenvectors and eigenvalues, we have singular vectors and singular values. So the columns of U are what we call the left singular vectors. And we call them the left singular vectors because they're the singular vectors in the matrix that's left of the center. You know, it's the one on the left. So I call these the left singular vectors. And this might seem totally random and a little confusing, but we'll actually talk about how we can compute these and why it's different than the things in V shortly. V, on the other hand, has the right singular vectors, which are different than the left singular vectors, which is different when you compare it to eigendecomposition, where both of these have the eigenvectors. And actually, the eigendecomposition can be thought of as a special case of a singular value decomposition when U and V are the same. But that doesn't really matter right now. So U and V are different, and they have different singular vectors, the right singular vectors and the left singular vectors. D, as we said, is diagonal, and along this diagonal are going to be these singular values, which are kind of the kind of SVD analog to eigenvalues. So these are going to be the singular values, which instead of being denoted with some lambda with the eigenvalues, we denote it with a sigma. That looks like this. All right, so we're going to actually visualize this a lot more and talk about how do we actually calculate these throughout the lecture, but I think first it's a good thing to come up. First thing, it's good to show a kind of geometric intuition of what these matrices do and how they transform space. So essentially what we can do is we can draw some two-dimensional space, and I can just plot any two vectors in them. So say this one and this one. These aren't necessarily orthogonal to each other, they aren't necessarily the same length, they're just two randomly placed vectors. We can understand A to be a matrix, but we can also understand it to be a linear transformation, as we learned in our linear transformation video. So if you multiply the space by A, or if you think about transforming the space by A as multiplying every possible vector in this entire space by A, you'll get some resulting space that looks very different than this, and these two vectors will be pointing in very different directions with different lengths and all sorts of different stuff. So let's transform the space by A and see what the resulting space looks like. And the reason why I'm doing it over here will become clear shortly. So say we get this and this instead. So that's after we transform it. So let's label these for completeness. I have so many markers, it's getting tough. So we get some V1 and some V2. And again, we have some V2 here and some V1. Let's say that's the transformation. So the matrix A encodes this transformation. So essentially, we can kind of get from here to here in one swoop with A. So A does all the stretching and rotating and all of that stuff required to these vectors to get it from here to here. One trick that we introduced in the eigenvector eigenvalue lecture is that we can kind of draw a little circle around this. It's not necessarily a unit circle because we don't know what length those are, but some circle around these points. And then we can draw some circle around these points to kind of better visualize how these vectors get distorted and in a way how this circle gets distorted by the transformation. Okay, so basically we understand that getting from here to here it takes one transformation A. One matrix linear transformation from this to this takes A. And that A encodes that transformation. But what we learned here is that for any A, and that's now any A, it doesn't have to be square anymore, it can be any A, can be broken down to three separate matrices. So that can be understood as any transformation can be split into three separate, smaller transformations. So you can think of, instead of doing it in one fell swoop, we can kind of separate into three special steps that do the exact same job as A. Because essentially what we're saying is if we kind of transform this space by V transpose, and we generally go from right to left in matrix multiplication. So if we transform this space by V transpose, and then we transform that space by D, and then finally we transform that space by U, we should get to this. Right? And we'll kind of show, and what I'm going to show is exactly what each of those matrices do. Okay, so let's do the V transpose first, because that's the order. So generally, and I never really mentioned this, but it's a quick little thing to talk about, and I won't tell you why really here, so I'll ask you to kind of trust me on this one. But there's a lot of information, lectures, and resources out there that you can use to confirm this. But essentially, an orthogonal matrix, and remember that's a matrix with orthonormal columns, is something that rotates space. So say if you have two vectors like this one and this one. If you transform the space by an orthogonal matrix, if you do a linear transformation encoded by an orthogonal matrix, all you're going to do is you're going to rotate these two vectors in some direction. So say you're going to have them like this and this now. It's kind of weird because they look a little different, but just imagine these being the exact same length. Try to make them a little more similar. Sure. So you transform like this to this. And the thing is that when you multiply or you transform by orthogonal matrix, the lengths of these are preserved, so the lengths of these are exact same. So say this is some V1, V2, and some V1, V2. So I guess this went all the way around that way, so it went like this. So that means this V1 is the exact same length as this V1, and this V2 is the exact same length as that V2. And otherwise, crucially, the angle between them is also preserved. So this angle is the same, and this angle is the same. So it's just a rotation. So multiplication by some orthogonal matrix is simply a rotation. That's a geometric understanding. So we know that V transpose is an orthogonal matrix, so we know that the first step is just going to simply be a rotation of this space. So let's do that. So let's draw that out here. So V transpose is our first step, right to left, and let's draw this out. So let's say this rotates them a little bit to the left, a little bit, I guess, counterclockwise that would be, and this makes them go like this, and let's say it makes them go like that. So that's the exact same vectors, and let's label those once again and put our little circle around them. So this is V2, and this is V1, so we just kind of move them a little bit to the left here, but they're the exact same length and the angle between them is exactly the same. So theoretically this circle here should be the exact same circle as it is here. which is not because my drawing isn't perfect, but you get the idea. Okay, so a circle hasn't changed, the actual lengths haven't changed, and the angle between them hasn't changed, just have rotated. Now what does this next step do? What does D do? Okay, well D, what color should I use for this? Maybe I should use a nice green for this, there we go. Okay, so this next step is D. And what does D do? Well, we can go back to kind of thinking about what we first learned when we learned about multiplying something by a diagonal matrix. And often when we multiplied something by a diagonal matrix, it was quite nice, right? Because we only kind of thought of it as almost an element-wise multiplication, because we just multiplied the resulting thing by the rows of the diagonal matrix. And remember, it was quite nice. So you can kind of think of it as scaling a vector, right? Because remember, we thought of it as kind of element-wise multiplying a vector and kind of scaling a vector. And you can think about it that way here too. So you can think about this kind of step by multiplying. I'm kind of struggling to open this because I'm carrying way too many of these. Let me just put some of these down. Let me put some of these down. So we can think of this diagonal step as scaling the matrices in some way. So multiplying each matrix by some number to either shrink it or stretch it, and even make it point in a different direction. Something that often gets confused is that you're just scaling the vectors and they preserve the angle width in between them. But actually the angle width can change. This can end up pointing in a different direction and the angle can get shorter or wider between them. So it doesn't preserve angles, but it kind of scales and stretches them in a sort of way. So this can be thought as this kind of scaling and stretching step. So D now scales and stretches them. So again, this might not preserve angles, this is just a scaling and stretching step. So let's say this makes the right one shorter, so it kind of squishes it. And then makes the left one longer. And maybe it even pulls it a little bit closer together, right? Because now this angle is a little bit closer together. So maybe it changes the angle as well too. Let's make this a little longer. Right, so now we have these vectors here. And again, let's label those. So we're going to have some v2 and some v1 here. So this D is essentially just stretching and squishing them, not preserving angle lengths, just kind of changing the lengths of them and the directions of them, kind of doing a bunch of funky stuff there. Okay, so now we have this first step where we rotate them, and then we have this step where we stretch and scale them, and then let's draw the circle around here. Great, so we have that. Now, let's do the final step, and that's U. And remember that U is also orthogonal. So that means this is going to be another rotation. So that other rotation is going to take us to here. So essentially, we can break down any linear transformation into a first rotation, then a stretching and scaling, which is kind of the most important part, because it makes the things look different, and then another rotation step. And that gets us from here to here. And multiplying by V transpose, D, and then U is the same thing as getting straight from here to here with A. So if we're analyzing these circles, this circle and this circle have to be the same kind of size and length. And this circle and this circle can be the exact same size and length. So that's kind of the geometric intuition of what we're doing here. And it's also just a nice thing to think about that any single linear transformation can be broken down into just 3 steps. Any linear transformation can be broken down into these steps. So it's just a nice thing to think about, and it's also really nice to have this geometric understanding. But right after this, we're going to actually talk about the algebraic kind of understanding of how we can actually calculate those U, D, and V matrices. So let's get to that now. Alright, so let's begin kind of tackling this algebraic intuition and how we can actually calculate U, D, and V. I owe this kind of intuition to Professor Gilbert Strang at MIT, who used this technique in his lectures to describe singular value decomposition, and I found it really intuitive, so I wanted to use it here too. So let's figure out how to calculate D and V first. So let's say we have A, which is this, of course, and we just want to make, just for fun, let's try calculating A transpose A. And let's just try replacing the definitions of A with the definitions here. So some U, D, V transpose, and then U, D, V again. Sorry, with transpose here. And you might have remembered, or you should remember from one of the articles up there that I made you read that talked about how to transpose products of matrices. Essentially, you just flip this on the inside and then you transpose each thing. So this becomes V, D transpose, U transpose, and this stays the same, U, D, V transpose. Notice here that since U are orthogonal matrices, U transpose U is just the identity, because U transpose is the equivalent to the inverse. So we get V, D transpose, D, VT. So we get that A transpose A is equal to this. Further, remembering that diagonal matrices are by default symmetric, just if we look at something like A and B, 0 and 0, or some diagonal thing, automatically across the diagonal is mirrored because everything off the diagonal is 0 anyways, which technically means they're the same off the diagonal, they're symmetric. So we can tell that VD transpose is going to be the same as VD and then dVT. So this is going to simplify to some VD squared VT. Remembering that when we first talk about eigendecompositions and an application of eigendecompositions, that when we square a diagonal matrix, or in fact when you take a diagonal matrix to any power, so if we take this to the nth power, we simply just take every element along the diagonal to that same nth power, and that's how we calculate that same matrix. So this is essentially just some matrix D with each of the elements along the diagonal squared. But now we can notice the critical thing, that A transpose A is equal to this. But this is an eigendecomposition. We have some V and some diagonal matrix and some V transpose. In fact, it's kind of the nicest case of the eigendecomposition of a symmetric matrix. That's why this is a transpose, not an inverse. So essentially, V, in the context of treating this like an eigendecomposition, V, the columns of V are going to be the eigenvectors of A transpose A. The columns of V are going to be the eigenvectors of A transpose A, the unit eigenvectors of A transpose A. Same thing with this V here. And now the D squared, the D squared is going to be the eigenvalues of A transpose A, which means that D will be the square root of the eigenvalues of A transpose A. So let's write this out here, because now we know how to calculate V, and now we know how to calculate D. So let's calculate V over here. Let's say how we calculate V over here. I'm going to make a little more space, because I'm going to draw three things here. So here in the V, we're going to say how we calculate V. So we calculate the right singular vectors, so right singular vectors, which is the columns of the matrix V. And we do that by calculating the eigenvectors of A transpose A. Because we can see with this intuition, it just breaks down to an eigendecomposition. And then we know by the format of an eigendecomposition that V must have the columns that are the eigenvectors, the unit eigenvectors of A transpose A. It's going to equal unit evex of A transpose A. So isn't that nice? And then furthermore, D squared, or the singular values, are going to be the square root of the eigenvalues. So we're going to say over here, so we're going to say singular values are going to be the square root of A transpose A. So that's just simply the square root of the eigenvalues of A transpose A. Okay, so that covers everything except for U, which is the left singular vectors, and that's what we can calculate now. So let's just get rid of all of this. And now let's play around a little more. So A transpose A worked really nice for us. We discovered that cool fact. But let's try AA transpose now. See if we can figure out something else. AA transpose. Now let's replace A with the UDV transpose kind of definition. So we're going to get some UDV transpose, and then some UDV transpose again, but this is transposed. And then this stays the same on the left here. And then we flip this and transpose it, so we're going to get some V transpose transpose, which is just V, and then we're going to get D transpose U transpose. So now we realize in the middle that this is an orthogonal matrix multiplication, so this just becomes the identity. So we get some U, D, V transpose, sorry, the V transpose gets canceled out, some U, D, D transpose, and then U transpose. Again, we can use the same intuition that D transpose is the same as D because they're diagonal and therefore symmetric matrices, so we get some U, D squared, U transpose. So AAT is equal to this, AA transpose is equal to this. And we see again that this is another eigendecomposition. We have some matrix here and then some matrix transpose here, so it's actually an eigendecomposition of a symmetric matrix, which tells us that AA transpose is a symmetric matrix as well. And now we learn that U is simply the eigenvectors, the unit eigenvectors of AA transpose. So let's write that down. Left singular vectors are going to be unit evex of AA transpose. So let's kind of underline those here. And furthermore, that we realize that D squared appears again here. So again, the singular values are also the square root of the eigenvalues of AA transpose as well, of this or AA transpose. So either way. So isn't that beautiful? Isn't that nice that we can calculate this entire very powerful SVD just by using the tools of eigendecomposition we learned earlier? So that's really all that I need to talk about here. So let's erase this and do a quick recap at the end. So, to do SVD, we want to decompose some matrix A into three component matrices. This is U, D, and V transpose. And U is comprised with the columns of U are the left singular vectors, the columns of V are the right singular vectors, and the things along the diagonal in D are the singular values. We calculate L, we calculate U, or the columns of U, as the unit eigenvectors of AA transpose. And those are the left singular vectors. We calculate the singular values, or the thing that go along the diagonal, as the square root of the eigenvalues of A transpose A or AA transpose. And finally, to calculate the columns of V, which become the rows of V as you transpose it, but to calculate calculate the columns of V, or the right singular vectors, we calculate the unit eigenvectors of A transpose A. And it's that simple. That's how you calculate singular value decomposition. Thanks for watching this, and I'll see you in the next lecture. Bye!